Thank you for the introduction, Katsuyo, and thanks to the organizers for having me. It's always a pleasure to be here at IPAM. So I wanted to tell you a little bit about some work we have been doing in the past few years on an inverse problem where we are interested in looking at interacting particle systems or agent-based systems. I'm not going to differentiate very much in this talk between particle and agents. By agents, I mean something more complex. It could be a cell, it could be a human or an animal, and so on. Everything I'm going to discuss is sort of applies to both particle-based and agent-based systems. And the basic problem is essentially given trajectories of an interacting particle systems, how can you go about estimating the interaction laws of that system? And here's a movie I grabbed from YouTube by Felix Munoz about Stirling, a murmuration, I guess it's called, of Stirlings. And you see you have all those agents, I guess. One bird is an agent. You have probably thousands of them moving in 3D. So the state space of this system is 3,000 dimensional, and the phase space twice as that. And, one would think that every one of these birds is not, really seeing the global patterns of all of the others. Is probably interacting locally with nearby birds and somehow making decisions about how to change their velocity. And nevertheless, there are also emergent patterns which are ordered. There is almost a nice surface in 3D evolving in time. All right, so let me tell you a little bit about the problem setup. We're going to look at toy models here. So these are some of the toy models that are going to reappear later in the talk. We might be interested in some models from mathematical ecology for prey and predators. Here there are multiple preys and one predator. Here is a model for in 2D for fish milling by Bertozzi, Ursola, and others, where fish start in a disordered state and then they form a pattern of milling. These are prey fish. They supposedly do this to confuse the predators. And one of the features here is actually that some fish are milling clockwise and some others counterclockwise. And here is a very simple system in 2D again of particles interacting with the Lennard-Jones potential, so highly repulsive to avoid collisions in the near field and attractive in farther away. But it's also a stochastic system. You see that these particles move somewhat erratically, so at every time step there is a random kick of Brownian motion on that. And the problem is, one might start with casting the problem in the following way. You have a dynamical system. The state is represented by X. In the case of the birds, 1,000 birds in 3D. So this vector X is the set of all of the coordinates of all the birds. So it's 3 times 1,000 birds dimensional, so 3,000 dimensions. And we write a system of ODEs, say first order, without much loss of generality, actually. I'll talk about higher order later. And the velocity is simply a function of the current state. So this function f is a function from Rd to Rd, mapping states to the corresponding velocities, which of course have the same dimensions. So in the case of the birds, it would be a function from 3,000 to 3,000 dimensions. And we're going to assume we have observations of trajectories of this system. And the observations of the trajectories are going to be in the following form. So suppose this is the first trajectory indexed by m equal to 1. And along that trajectory, we're going to observe some positions and the corresponding velocities. And then we're going to have a second trajectory, m equal to 2, with the corresponding positions and velocity measured at different times.
Can I ask a quick clarifying question?
Yeah, absolutely.
Are you explicitly assuming here that f depends only on x and not on the current value of x dot for this purpose?
Yes, just first order. Yes, that's right. Yes, so it's already put in explicit form, if you wish. That's right. Yes. And so I'm going to use the index m to index trajectories, and L to index the times TL at which we're going to observe our positions and velocities. These TLs are going to start from 0 without loss of generality, and they're going to end at some time capital T. And the goal is, given this data, we would like to construct a function, f which is close to the unknown function f, right? We're only given data and we want to construct f. There is nothing random about this problem, so right now it's almost an approximation or a fitting problem. But randomness arises naturally in various ways. So for example, the measurements of positions and velocities could be perturbed by noise, which would add randomness to the problem. Another source of randomness is the following. So probably we can, in general, we cannot control the initial conditions of the system. Of course, if these are simulations, maybe we can, but if we're observing agents in the wild, we cannot set the position of a bird from which the trajectory is going to start. So maybe the initial position of the system should be also considered not under our control and should be modeled as random. And I'm going to do that throughout the talk. So I'm going to assume that the initial positions at time t1 of the system along any of the trajectories at m is going to be random, drawn from some measure in R capital D, a probability measure from which these initial conditions are sampled. And these initial conditions are assumed to be all independent from each other. So the observation of the trajectory I make today has an initial condition that has nothing to do, quote unquote, with the initial condition of the observations I'm going to make tomorrow and the day after tomorrow and so on.
What is the n indexing of f hat n?
Oh, thank you. Yes, I didn't say it on purpose because it might be confusing, but so in statistics, we like to remind ourselves that this estimator depends on the data. So I should really write this f hat depends on all of the data that I have here. I don't want to write that, so I'm going to put this n to remind myself that I have n data points, and the small n over here will be equal to the number of trajectories that I have times the number of times on which I'm observing along each trajectory. So this small n, the amount of data that I have, is capital N times capital L. Thank you. Okay, thank you for your questions. And we're also interested in the case where we want to know very little about the function f. And so we're going to play a game in statistics that is called the non-parametric game, where we're going to assume only that f has some regularity, maybe it's differentiable, but we're not going to make specific assumptions about the form of the function f. Not that we don't welcome suggestions about which form the function f might have, but we're interested in situations where we might know very little about f. All right, so this might remind you of the problem of the regression. For those of you who are not familiar with it, or just the language, you're probably familiar with it, but maybe not in the same language. So the problem of the regression is a fundamental problem in statistics or machine learning or AI, however it's called. So it's a problem where you're given pairs of inputs and outputs. Let me call my inputs Zi, the outputs f of Zi, perhaps corrupted by noise. So these eta i's are just noise realizations. And the inputs Zi are in some space R capital D. This is going to be the same as in the previous setting, of course. So the Zi's are going to assume to be random and sample from some probability distribution. Here I plotted the density of the probability distribution with respect to which the Zi's might be sampled. So it's bimodal, so Zi's are more likely to be here and over here and less likely to be over here and over there. And what we're given are these pairs. So this plot is in RD cross RD. Our function is also taking values in RD. And what we're seeing are these pairs. Here I have no noise, and these pairs lie on this surface, capital D dimensional surface of the graph of f. And so in regression, we're given these n inputs and corresponding outputs, perhaps with noise, and we're interested in constructing our estimator. And this is a classical problem. It's very well understood in many cases. And one of the things that one can do is construct f at n estimators such that are good. How is that measured? Well, so f is a function, f at n is another function, so you need a distance between functions. The typical distance that is picked is the mean square distance with respect to the measure rho of the inputs. This is what this L2 rho represents. And f is given, but f hat is random with the data. So this is a random distance. We can measure the average of it. The average over what? The average over the input samples and over the noise, if there is noise. So the left-hand side is this mean L2 distance between the true F and the estimator. And one can construct this estimator so that this average distance is smaller than this quantity. So S measures the regularity of F. So if F is C1, S is equal to 1. If F is C2, S is equal to 2. But S can also be just a real number for Holder regularity. And the nice thing about this right-hand side over here, it's n to a negative power. So as n goes to infinity, that goes to 0. That says that the estimators that get constructed do converge to F, at least in this notion of distance and in this mean sense. But what about the rate of convergence? Let's fix S equal to 1, so F one-time differentiable. Then this exponent will be 2 over 2 plus capital D. Capital D is the dimension of the inputs and the outputs, but that's essentially immaterial to this. The fundamental thing is that D is here in the inputs. And when capital D is very large, this exponent becomes very close to 0. So this is n to the minus a very small number. It's a very slowly decreasing function. And if you wanted to make the right-hand side smaller than epsilon, you would need about 1 over epsilon to the D samples, which is a lot, right? As soon as epsilon is, say, 1/10, this is 10 to the capital D. If capital D is 1,000, that's 10 to the 100, 10 to the 1,000. So this is an instance of the so-called curse of dimensionality. And it's called the curse of dimensionality because, you see, I haven't told you how we construct this estimator F at n. I just told you there are many ways of constructing them in such a way that this inequality is satisfied. But in fact, the news is much worse in the sense that it is impossible to construct an estimator that converges at a rate which is better than this. Nobody will ever be able to construct an estimator with a better rate of convergence, no matter how many computers you use or how deep a network you construct or whatever. And under the assumption that the only thing that you know is that F is, one-time differentiable. All right, so if we go back to our problem and we instantiate and we try to view it as a regression, well, we have our inputs, the positions inside the argument of the function f on the right-hand side, where the output, the velocities, which we also observe. So this seems a straight regression problem. There is actually a slight issue over here. In our regression problem, the inputs were sampled independently from some measure, which I called rho in the non-parametric regression slide. These samples over here are far from being independent. If we look along a trajectory, the samples are completely dependent of each other. This is a deterministic trajectory. If you know the initial condition, you know all of your other observations that you're going to make. So there is no independence along each trajectory. But there is independence, so no independence in the index L, but there is independence across trajectories because every trajectory started from an independent initial condition, and so there is independence there. But if we throw this away or overlook this as a technicality, and we pretend that our observations were independent, we're still in a very bad situation because in the case of interacting particles, for instance, the dimension of the space is huge, right? You have capital N agents in the dimensions, 1,000 birds in 3D, capital D is 3,000. This rate over here, which is unbeatable, is about n to the minus, say, 1 over 3,002. Completely useless. All right? So this is inescapable, again, if the only assumption that one makes about the function f is that it has a certain regularity. But in the system that we consider here, this is a general system of ODs. We actually have not put in the information that this is an interacting particle system, that this is made of particles that are interacting with each other. So let's put that information in, and let's see whether that assumption actually changes the situation. So I'm going to consider the simplest example of all, and then I'm going to tell you that this generalizes really a lot. And this is all joint work with Fei Lu, Sui Tang, and Ming Zhong, and then other people that I'm going to mention later. But these are the people we got it started with. So let's assume that our system is really made of particles that interact. And so the index I is going to be indexing the particle, the ith bird. And the velocity on the nth trajectory at time t is going to be given by the right-hand side. The right-hand side is an average of interactions between xi and its peers, indexed by I prime. And this right-hand side has two terms, a scalar term, this phi of the distance between xi and xi prime, and a vector term, which is xi prime minus xi. So xi prime minus xi is a vector pointing in the direction connecting the ith agent with the I prime agent. And phi of the distance between the two agents is a function called the interaction kernel, which is giving the strength of interaction between xi and xi prime in the direction connecting them. And then the total effect on the ith agent is going to be given by averaging all of these pairwise interactions between the ith agent and the I prime agent. This function phi is, so if we assume that we know that the right-hand side is in this form, then the only unknown is the function phi, and the function phi is just a function of one variable, right? The pairwise distance between agents. And that sounds good in terms of the Cursor dimensionality, because now the dimensionality of the inputs of the function we're trying to regress is just one. But something has changed, fundamentally changed. Before we had a regression problem, if you wish, a direct problem, where we had inputs and the corresponding outputs. This is not the case anymore here if we're considering our function phi as being our unknown, because I think I underlined this, yes. So I underline the things that we know. So we know the spatial structure of the right-hand side. We see the velocities. We see the position. So we can compute this. We can compute the pairwise distances. So we know the inputs of the function phi. We had them in our data. But we never see phi of any given pairwise distance. All we see is this average of many phis of pairwise distances multiplied by these vectors, because that's the left-hand side that we see. And so the problem is not a direct problem anymore. What we're trying to estimate, the function phi, is hidden from us. We don't have direct measurements. And in fact, it's hidden inside an average. And it doesn't sound like such a good idea to try to estimate what's inside an average by having measures of the average itself. But the Cursor dimensionality is such a curse that we're going to try to do that. All right, so this is going to be an inverse problem, because somehow we would like to invert this average to get to the values of the function phi and the function phi itself. All right, so we definitely need to use time here. If you count how many variables you have at any given fixed time, you can't invert this sum. You really need to use time. And in order to make at least mathematical sense of things, we are going to have we need to have a function space in the non-parametric regression setting that I recalled. We had an L2 of rho, where rho was the distribution of the inputs. Here we need something like that in order to measure how well we're going to be doing. So we're going to construct a measure rho. It has a formula which seems ugly, but it's actually really, really simple. All I'm doing is the following. I have my trajectories with all the birds flying, and at every time and on every trajectory, for every pair of birds, I measure the distance, and I drop a delta function on the positive real axis corresponding to that distance. That's what this ugly thing is. It's just a delta function at the pairwise distance between agent I and I prime on the mth trajectory at time tl. And then I'm going to average over all pairs of birds. That's this average over I prime. I'm going to average over all the observations in time, and I'm going to average over all initial conditions. That gives me a measure on the positive real axis, and that's the measure with respect to which we are going to measure our performance. So before I go further, I wanted to mention that there are connections with some themes that we already touched upon in the first workshop and in the tutorials, which are mean field limits. This was work with Massimo Fornazier and other collaborators. So it is, in this case of interacting particle systems, especially in the case where all of the agents are identical to each other, a very natural operation that one can do when the number of agents is very large is to let the number of agents go to infinity. And what happens? Well, you can think that when you have n agents, you can replace the n agents by thinking of them as being a bunch of delta functions on top of each agent, rescaled by 1 over n. So you replace the thinking of the agents as being in n positions by them as being, on a discrete measure with n normalized delta functions. And then when you let n go to infinity, this average of delta functions, this measure mu n, hopefully tends to a measure mu. And the measure mu is the density of the agents. Think of the flocking birds moving as being a density on a manifold that changes in time. That's, if it was continuous, if the number of birds is going to infinity, that would be a continuous manifold with a measure on top. And you can write a PDE for the evolution of that measure. And the interaction kernel phi up to essentially anti-differentiating it appears also in that mean field equation. And you could study the problem of observing solutions of this PDE and trying to infer the interaction kernel there. My colleague Fei Lu in the math department has done some work in this direction. So this is the direction where the number n of agents goes to infinity. What I want to discuss in this talk is when the number of agents is fixed, but we have more and more observations. We have more and more trajectories that we observe.
Is star here the
Yes.
convolution?
It is, yes. So the convolution arises essentially because this kernel is translation invariant, and so when you take the limit, the convolution appears, yes. So here's an example of that measure that I just introduced. So these are 7 particles interacting with Lennard-Jones in 2D. I observe them up to some time capital T. And this histogram over here is a representation of the measure rho. So this is saying that if you look at pairwise distance between particles, particles never collide, right? There is nobody really, really close to 0. I often see particles with a pairwise distance just above 1, somewhat often particles with pairwise distance about 2, and so on. And this picture is just to tell you that this measure is not uniform. It does feel the effect of the interaction kernel, and but it's also not that terrible, right? I mean, it's kind of spiky, but it has some regularity, and some things about its regularity can be proven. All right, so how are we going to construct an estimate for our interaction kernel? So we make first the trivial observation that if we look at our right-hand side, this whole thing, we can write it as an f indexed by the interaction kernel phi. And the observation is that this function f sub phi is linear in phi, right? So f sub phi1 plus phi2 is equal to f sub phi1 plus f sub phi2, just because this whole thing is linear in phi. And then we do the simplest thing possible, or start by doing the simplest thing possible, and then we're going to slightly regularize it. So we don't know the interaction kernel phi. Suppose we guess it. Let's call psi our guess. And let's introduce a functional that measures how good psi is. And this functional should be something that we are able to compute from data. And so this is a functional that we use. It's a least square functional. It's the simplest functional you can come up with. Gauss was using it a lot. And what is it measuring? Well, this is the left-hand side of our system of ODEs. This is the right-hand side of a system of ODEs with interaction kernel psi. Here, we look at the difference between the left-hand side and the right-hand side of that dynamical system with psi as interaction kernel. We measure the difference between the right-hand side and the left-hand side squared. And we sum overall agents, overall trajectories, overall times at which we make observations. All of these can be measured from data. We had these, the velocities, we have the locations. For any given choice of psi, we can compute this. So this can definitely be evaluated for any given psi on data. And we would like to make this small. In fact, if this functional was exactly 0, then our velocities would be f sub psi of the positions. And when psi is equal to phi, that difference is exactly 0 for all times, for all agents, for all trajectories. So minimizing this seems like a good idea. But we would need to minimize overall psi's. That doesn't really make sense. Psi is an arbitrary function. There are too many of them. And so we're going to regularize the problem by constraining psi to be on a finite dimensional subspace of functions. So we're going to choose a hypothesis space, H, of some dimension n. I apologize, the small n has nothing to do with the small n that I used in my regression mini tutorial. So this is going to be the dimension of the hypothesis space. And our estimator is going to minimize this functional over all choices of psi in this hypothesis space. Well, how do we pick this hypothesis space? I'm going to tell you in a second, and what can we say about how good the estimator is. All right. So we have this problem. We want to minimize a function on a finite dimensional subspace. One can ask, is there a solution, and is the solution unique? We find conditions for which that is true. I'm not going to parse them here, but I'm very happy to discuss later. These are ugly-looking conditions, but in fact, they're very natural. And not only do they guarantee uniqueness, at least when the number capital M of trajectories goes to infinity for the solution of the problem, but they also tell you how ill-posed this problem is, right? We're doing an inverse problem, going from data, sort of extracting something hidden inside, that function phi. It's good to know how sensitive it is to perturbations, and so what the condition number of the problem is. And this sort of conditions completely allows us to measure what the condition number of the problem is, besides giving us uniqueness. So it's quantitative uniqueness, if you want. And then we're going to play the following game. This is the hardest part of the math in the talk. I apologize. This together with the following theorem, but there is a picture. Okay, the picture is the following. There is the space of all possible functions, which are square integrable with respect to our measure. Maybe inside there we pick nice functions. This KRS is, for example, differentiable functions with compact support. And our unknown interaction kernel phi, which we're trying to learn, is somewhere in there. We pick some finite dimensional subspace, because that's all we can do statistics with and compute with. And inside H, we're minimizing these functions. And that's what our phi hat, our estimate for phi, is going to be. So it's going to be some point in the subspace H. And we want to know how far is phi hat from phi. Well, you just use Pythagoras' theorem. You observe that you can do the orthogonal projection of phi onto this subspace. Orthogonal projections make sense in this L2 space. And obtaining pH of phi, which is the closest element in H to phi. And then there is a difference between phi and pH phi, and between pH phi and phi hat. And these two distances have completely different nature. Phi is not random. It's the unknown interaction kernel. Given H, pH of phi is what it is. It's the closest element to phi in that subspace. So this is the difference between phi and its projection onto H. It's called the bias. You chose a model. Phi is probably outside of the model. So you incur an error just because you chose a model, an hypothesis space H. The difference between pH phi and phi hat has a completely different character. Phi hat is random, and so it's going to be ideally pretty close to this pH of phi, but it's going to randomly sort of wander around pH phi. And so this distance is going to be random, and you want to control it. But for sure, by Pythagoras' theorem, the distance between phi hat and phi squared is just going to be the sum of these two distances squared. Now, this gives us an intuition about what should we do about H. We want to pick H large, so that hopefully the distance between phi and its closest approximating element in H is going to be small. So the larger H is, the smaller the bias. The larger the model, the less biased it is. But the larger the model, the more parameters we need to estimate to get phi hat. Phi hat has more opportunities to wander around pH phi, and its variance is going to be larger. So as we increase the size of H, the bias goes down, the variance goes up, and there should be a sweet point for how to choose H. This is what the game of nonparametric statistics is about. Nonparametric statistics is not about not having parameters. It means having infinitely many parameters and choosing the right amount of parameters given the data. The more data we have, the more bold we should be in the sense of choosing bigger H's, because that's going to reduce the bias. And if we have more data, the bias should be under control even for larger dimensional H's. And so one can get the following result. Forget the technicalities. The technicalities are about giving a bound on the bias. So we want subspaces H's that so we're not going to pick just one subspace H. We're going to pick a chain of increasingly higher and higher dimensional H's that get better and better at approximating any regular phi. So if the dimension of H n is about n, then in Hn, you can find an element which is this close to phi. We know how to do that very well from approximation theory. You can pick Hn to be the span of the n lowest frequency Fourier modes on an interval. You can pick polynomial, or say orthogonal polynomials of degree n. You can pick piecewise polynomials. You can pick wavelets. There are many, many choices that satisfy this technical assumption, and we know a lot about those. And then he says, well, if you have this chain of subspaces, Hn of dimension each about n, and if you have capital M trajectories, you choose n equal to this n star, which grows with the data at a certain rate, depending on the regularity of f. So as m increases, we are going to pick higher dimensional hypothesis spaces. Then we can promise you the following, that the distance between phi and phi hat, okay, it's not quite the distance, so I apologize for the notation, but I can't tell myself. So this phi dot dot is just the function that evaluated at the pairwise distance r is phi r times r. Turns out that this is the right way of measuring distances between functions here in this context. So the distance between phi hat and phi satisfies this, again, in expectation over noise or initial conditions for the different trajectories, satisfies this bound. And if we look at this bound, well, there is an m in the denominator. The log m is much smaller. So as capital M, the number of trajectories that we have goes to infinity. This goes to 0. And it goes to 0 at which rate? The rate at which it goes to 0 is this s over 2s plus 1. Again, think of s equal to 1 for a one-dimensional, for a one-differentiable interaction kernel. But the point of this exponent is that there is no dimension. So the dimension of a state space was number of agents times the physical dimension small d. But there is no number of agents, capital N. There is no physical dimension small d in this exponent. The only thing that appears is this number 1. And there is a number 1 because the function phi is a function of one variable, pairwise distances. That's all that matters here. There is also a constant over here, which is our sort of cursivity condition that guaranteed uniqueness. So we track it, and it's right there. And of course, it's really bad when this constant is small. And that was measuring how ill-conditioned the problem is. I should also mention that this rate is best possible. So if you remember the one slide about non-parametric regression, the exponent there was s over 2s plus d. So here we're saying that we get the same exponent in dimension 1. So that exponent is just unbeatable. So the estimator is best possible. All right, it can be computed rather efficiently, almost linear time. And before I stop showing you equations and show you some movies, let me also mention something else, which is that, okay, maybe we're doing really well in estimating the interaction kernel, but is that helpful in predicting trajectories of the system? Because one might get worried that in this theorem, we're controlling this L2 norm between the true interaction kernel and the estimated one. The L2 norm is not a very strong norm. We're talking about dynamical systems, so maybe that's not good enough to control errors between the trajectories. And what this bound says is that if you look at trajectories of the original system, and you look at trajectories which are generated by running the dynamics with the estimated interaction kernel, that's what the hat here means, and you compare them over a finite time interval, then the distance between the trajectories can be upper bounded by the distance between the interaction kernels, phi, the true one, phi, and the estimated one, phi hat, in this rather weak L2 norm. All right, so this was the quantity going to 0 in the theorem, so trajectory is going to be well predicted. Now, this is mostly a math result in the sense that the constants over here are terrible, especially in time. They grow, super exponentially in time. These systems can be very sensitive to small perturbations. They can have large Lyapunov exponents, so there is no way that without further information we can get the decent constant over here. Albeit, we will try and we will run things for large times, but we're just going to cross our fingers. This theorem is not telling us anything good about that. All right, let me just show you some examples. And before I do that, since we might be interested in physics, we are not going to do first order equations. We can do higher when, for example, we could do second order equations. When when looking at the literature, interacting particle systems in 2D, maybe the simplest models now have different types of interaction kernels. One sometimes called the energy interaction kernel, that depends on the pairwise distances, Ri prime, times this vector Ri prime, which is xi prime minus xi. But they also have an alignment interaction kernel, which multiplies the difference between velocities. Birds might want to align as they fly. So that's one change when you go to higher order differential equations. We might have agents which are not all the same. For example, in prey-predator models, so we might have agents of different types, and now a prey-prey interaction is different from a prey-predator interaction, and that's different from a predator-prey and a predator-predator interaction. And so we have multiple interaction kernels depending on the types of the agents involved. This is what this subindex kappa I prime denotes. And we can have simple interactions with an environment, food concentration, light, for photosensitive bacteria and so on. Right, so the whole theory generalizes. Let me just show you some movies. So in all of these movies, so 2 columns and 2 rows. So the first column is the system run with the true interaction kernel. The second column is the system run with the estimated interaction kernel. The first row, it's a trajectory when the initial condition was in the training data, and the first row. And the second row has an initial condition that is completely new. And so we are particularly happy when this trajectory is close to this one, because that means that the trajectory from a new set of initial conditions run by running the dynamics with phi hat is close to the corresponding trajectory with a true phi. Oh, by the way, I should mention here that I'm always entertained by the fact that these prey-predator systems, at least that we borrow from the literature, this is a pretty steady state where the predator is surrounded by prey, is not quite sure which one to catch, and this is a stable configuration. This is, I guess, a more natural one where the preys are just running for their lives. I also look for mistakes in our predictions. So here are a couple of trajectories for which we make mistakes. In particular, this one down here. I'm going to rerun the trajectory. So just something happens at one point that the agents or the preys are slightly different. And if we run for very large time, well, we incur an exponentially in time error. So we reach this state rather than that state. That can definitely happen. And this comes from a very small mistakes in the interaction kernel. When you run for a large time, all bets are off. So of course, in nature, we have many such systems, flocking birds and milling prey fish. And again, against the spirit of our theorem about being correct for short times, we're going to run long-time trajectories for systems that have these emergent behaviors, where sort of order emerges, large scale, both spatial and in time, order emerges from local interactions. And we ask, do we predict the correct emergent behaviors? And the answer is that in many cases, yes. So this is a simple example of flocking from Cooker and Smale, where our system also flocks. This is a more recent example of flocking with anticipation dynamics by Ethan Tadmore and collaborators just a few years ago. So things flock, but their velocities don't become exactly parallel to each other, but in the same general direction forever. And we catch that behavior. I should mention, this is important, that in all of these situations, the trajectories that we train our algorithm on are extremely short. This would be one trajectory. All right, this would be the typical length. So we never see in our training data the emergent behavior, but we hope to capture it nevertheless if we run for large times with our phi hat. So this is a milling example. Again, the short trajectories never see any milling behavior, but we learn the interaction kernel well enough that the emergent behavior is preserved. If you ask about specific positions of single fish, they're completely wrong. These are predicted locations. These are the ones obtained by the true feed. They're wrong, but the pattern is the same. And of course, these patterns have evolved to be robust, and that's why our phi hats are good enough to reproduce them. We can do these things on manifolds. This actually can be relevant to physics. If you have a physical system constrained on, say, Lagrangian submanifolds, then we can do interaction kernel learning also on those manifolds. We also consider the stochastic case with Fei Lu and Sui Tang. So in the stochastic case, the system has the same form, but at every time there is a random kick by Brownian motion. So we cannot see the velocities anymore. The velocities are infinite at every time step, so we only have observed positions. Maybe I should have said that in all of the examples that I mentioned, we also don't observe velocities. We all observe positions, and we approximate velocities by finite difference scheme. Here, there is just no choice. We cannot observe velocities. We can only observe positions. And we pay for it. We steal guarantees on how close phi hat is to phi. But there is an extra term. So this term appeared also before. It was the bias. This term was the variance. This goes to 0 as h becomes larger. This goes to 0 as capital M becomes larger, the number of trajectories. But there is an extra term, which is sort of a discretization in time error. So capital T is the interval in time in which we're making observations. Capital L is the number of observations that we make. So this is sort of a delta T that separates every observation from the next in time, and it's there. So unless you observe more and more frequently in time, there is just no hope to recover the true interaction kernel field.
Where did the stigma go to? Your noise track?
Oh, inside the C. Yes.
Okay.
Yeah. I think we track it in the paper, but not in this slide. Yes. And so here are stochastic trajectories, and of course the realization of the forcing term or the noise is the same in order to compare, and we do pretty well. And same thing for 2D systems. All right. So in the 5 minutes that I've left, I wanted to tell you about more recent work where we consider a more general problem. This is always with Fei Lu, but also with Shong Wang and Chenju Lam, now at Duke. So we consider the case where the interacting particles are not all interacting with each other, but there is an underlying network. And particles can only interact if they're connected nodes on that network. So I represent my network by a matrix A, an adjacency matrix, with entries which are non-negative, and represent the strength of the connection between an agent and any other agent. And so it's an n by n matrix, where n is the number of agents as before. And the equations, in the stochastic case, the infinitesimal displacements of the agent on the ith vertex of the network is this average of interactions between the ith agent and the jth agent, but gone through the interaction kernel phi, but multiplied by aij. So if aij is 0, agent I and j are not connected to each other, so they don't interact. If aij is positive and large, then that enters in there, in the equation. Now, if we knew the network A, I could repeat everything that I did before, and I could estimate the interaction kernel. But here, we don't know both the network and the interaction kernel. So if this was an example of people exchanging opinions and changing their opinions based on their interactions, this would correspond to say, well, I don't know the interaction kernel, meaning that I don't know what happens when two people exchange opinions. But I also don't know who has been talking with whom, because I don't know the network A. And given trajectories of their opinions, I would like to infer both. So this problem is quite different. So here is a trivial example with 6 agents, directed connections between one and quote unquote the next one on this sort of circle graph. This is the network matrix, 6 by 6, mostly 0 and non-zero entry for these directed edges. This matrix is not symmetric. These edges are directed. So the system actually is not in conservative form anymore. I'm not sure what would happen about mean field limits here. the network will need to go to infinity too, and things are not directed. And this is a trajectory. So each x, say this is opinion dynamics. Each agent has a two-dimensional opinion, say about two one-dimensional opinions about two different topics, and they interact and they form this pattern where they actually never settle. They keep swirling around, which also shows that there is a lack of, it's not really a gradient system. So we can sort of repeat the same sort of ideas, but there is a fundamental difference, and it's all I'd like you to get out of this, is that now there are two unknowns, A and phi, and they're sort of multiplying each other. So the problem is not linear anymore. The problem that we were solving before was a linear inverse problem. We only had phi, and we needed to solve a linear least squares problem. Now, we have these two unknowns that multiply each other, so this is not a linear least squares problem anymore. It's sort of a quadratic one. And of course, the first idea, which is a classic, is when you have a non-convex, non-linear problem of this sort, you can try to alternate between variables. You can say, let me fix the network, learn the interaction kernel, fix the interaction kernel, estimate the network, and ping-pong back and forth between the two. And when we thought of this idea at the very beginning, we thought, okay, this is never going to work, but maybe we'll learn something. And it works amazingly well. So I'm not going to go through this, but we have conditions that guarantee that this works. As the number of trajectory increases, estimation errors for the interaction kernels for the network all go to 0, and we can predict the rate at which they go to 0. And we can do fun problems where you have a network, it's directed. This is still small. It's a 6x6 matrix. You have two-dimensional Lennard-Jones particles interacting with these weighted directed edges, and we estimate the interaction kernel, and we estimate the matrix. The error in the matrix is 10 to the minus 3, and the error in the kernel is of the order of 10 to the minus 2. So these are pretty decent accuracies. You can do much larger sizes. Right? This is, for example, a network with 128 agents interacting a la Lennard-Jones. This is the true A. It's a random, not so sparse matrix of interactions, non-symmetric or anything. This is a set of trajectories where things form swirling clusters. And we estimated the kernel and the underlying matrix, again, with error 10 to the minus 3. And similarly for the kernel. We have a lot of paths. I mean, we have about 1,000 paths here. This is a Kuramoto model with interaction kernel given by sine. If you squint at the trajectory long enough, you can see that, let me restart the movie. So after an initial phase, then the yellow agents stick together. They stick together, they move. They stick together, they move. They move, and they stick together. And the same thing happens to the blue and the red agents. So there is some amount of synchronization between the agents. And given a very, very short a set of very, very short trajectories where synchronization never happens, we can learn the interaction kernel and the network as well, and the synchronization behavior too. I'm going to skip this and this one too. And I'm just going to mention that in that paper and in a paper which is upcoming, we have considered also the case where there are agents on a network. We don't know the interaction kernel, we don't know the network, but the agents also have different types. And we don't know the type. And so there could be, if it was opinion dynamics, people who are very good at convincing other people of their opinions, people who are easily convinced and people who are not. And we don't know who is who. And we estimate all of that at the same time. In this paper, which is available in the archive, we did a simple case of that where we had a special case of different types of interaction kernels, but now we're tackling the general case. So many generalizations are possible, some of which we have done, some of which we're still working on. All of these interactions, so I mentioned pairwise distances, but already, I don't know if you noticed, but in the case of particles on a network, it was not pairwise distances, it was differences of the states between two agents. We can, essentially, we have a lot of flexibility in terms of a variable inside the interaction kernel. It doesn't need to be just a one-dimensional pairwise distance. It can be pretty much anything. The theorem goes through, the theory goes through too. The cursive dimension is going to come in, and it's going to be the the number of variables which are inside the interaction kernel is going to be the dimension, and you're going to be cursed by that dimension. So if you have pairwise distances and certain angles, then you have two variables, and everything goes through, except that the rate is going to have a 2 instead of a 1 in there. We're very interested also in situations where you don't know the variables inside the interaction kernel. Maybe you know about pairwise distances, but there might be other variables that you don't know, and you would like to figure that out. We wrote a short paper that just takes step 0 in this direction. It's a problem that I find fascinating, and I don't know how to solve. All right, thank you for your questions. I'm happy to answer more of them.